is School from Home, Watching the Wire with Wireshark. I'm Tony E. I'm here because I love packets. And you can find me on Twitter at @ShowIPInterfaceBrief. I'm going to bump up my notes a little bit so I can read them properly. A little bit about me before I get started. This is my first time presenting here at SharkFest. I attended SharkFest virtually last year, had a blast, and I'm always focused on little research projects with capturing packets and analysis. So throughout the year, I was doing one, and I thought it would be a good topic to share, and so that's why I'm here. I'm a network engineer by day. I'm CCIE 64908 in routing and switching. Now that's been moved over to the enterprise infrastructure track. I'm also Palo Alto certified. I'm a consultant focused on security architectures, engineering, and implementation. That's my day job. For most of the time outside of that, I'm still engineering, I'm still playing with things, and especially packet analysis. So I have my network forensic analyst certification from GIAC, and I typically run full PCAP at home. I love, what was then Moloch, now Archemy, and Suricata. I got to give Suricata some love. So I'm running inline IPS here on my home router in a container. So very cool stuff. I love playing around with packets, and I think I have a fun presentation for you guys to share. Like most people have lived through, the last 16, 18 months has been the COVID-19 pandemic. And working from home, we've also had to deal with school from home. And so my home network is my lab. Actually, probably every network is my lab. I just have a little bit more freedom on the one at home. Like I mentioned, I typically run many different tools in my home network. I run a SIM, some sort of SIM, if it's not ELK or Graylog, or at a minimum, a syslog collector, full packet capture, Suricata, Zeek, and TopNG. So I always have a lot of tools on my network for fun and for profit. And with everyone working from home, I couldn't help but start to, refocusing those tools on what was going on here on my home network, right? The kids have school issued Chromebooks that they brought home. So what was all this new traffic that I was going to be seeing? And what was I able to see from it? So I'm here to share with you what I found on my home network when the pandemic pushed all of us to do everything from home, and how what I found led to discovering some gaping holes in web traffic visibility and traffic security, web traffic security, if used maliciously. So I'm going to try and let the data do the talking and try to build some context around it. Like many presentations, I'm sure you've heard, I've been an attendee of Wireshark, and I've heard this a number of times. Wireshark is not always the best tool to get a big picture view. Typically, you want to use different sets of tools, and there are lots of different tools out there. It's like everyone just has their favorite flavor. And when I was building some of the research for this presentation, the flavor of the month for me was Brim. I absolutely love Brim. So like I said, I run a lot of tools at home, and allows me to get a big picture of what's going on the network. So in this case, Brim was my tool of choice to really start sort of hacking away at the traffic I was seeing before I took Wireshark and really focused in on what I was seeing on the wire. So I first noticed what was then an anomaly to me when I was looking at some dashboards in my SIM while focused on HTTP traffic. Now, this isn't like a global anomaly. Everyone else isn't seeing this, but it was an anomaly for me, for my baseline, and according to me, the only person who's watching my own wire. So I started seeing an HTTP verb that I wasn't used to seeing. I was fully prepared to see tons of gets and posts, typically more gets than posts, but I wasn't sure what connect was. So I marked that in my mental checklist of items I needed to correlate and search for context, and I continued to move on. So HTTP connect by itself, while is a bit out of the ordinary for my baseline, doesn't send me like running for the hills that I need, that I need to stop what's going on my network. I need more context. I need to understand. So I need to know who, what, where, when, why, and how, and of course, any other related events according to that traffic. So before we move on to another interesting item, in this screenshot, the destination ports column is labeled ID RESP underscore P for responder port. And all of these connections, these are web connections, right? This is a summary, a small chart of HTTP traffic using Brim. All of these connections seem to be going, I say all, not all, most of them seem to be going to non-standard ports, right? Except for the 584 unique connections using GET on port 80. Everything else is a non-standard port. So this is going to help clue us in, right? Another thing we need to keep track of. So we go digging a little bit more. So now I'm using Brim in this screenshot, and I'm looking at the HTTP logs, and I'm specifically looking for the HTTP method connect, as opposed to get or post or head. And I'm just going ahead and counting those, and then sorting and counting again. And at this point, I wasn't even really searching for context to define what connect was. I was still trying to just get a high level understanding of what is now going to become my new baseline. So other HTTP dashboards revealed even more strange data that I will soon learn is all related. And the reason this threw a red flag to me is when your browser is requesting a simple .com site, google.com, assuming it's using a clear text protocol and not quick, right? The URI for that is just a / right? It's get /, while the HTTP host actually will have www.google.com in it. That contains the FQDN. These components together make the full URI. So what's unique about this is you typically don't see the URI including the FQDN and the port, and you also typically don't see the HTTP host header including the FQDN : and the port number, right? The port number that your browser uses to initiate those TCP connections is normally determined by the scheme. And the scheme is that HTTP : / for TCP port 80 and HTTPS : / for TCP port 443. So it's a little bit out of the ordinary to see that here. But again, this is all going to circle back around and all becomes related. I see here in the chat, 8009 is Chromecast. Those two Chromebooks your kids are using. Yeah, thank you, David Holt. So this was interesting too. A huge, this is another screenshot. And again, I'm using Brim here. I don't remember exactly what my filter was. I think I was, again, looking at my clear text HTTP traffic, and I was probably just searching for star.pack. Because you just have sort of an intuition when you're looking at a long series of logs. And when I saw that pack file, something stuck out to me that said, you need to remember this. And again, so I went back and searched for it. And so this was interesting. A huge volume of today's traffic is TLS or QUIC. So anytime I'm in a network that happens to be logging clear text protocols like DNS, FTP, Telnet, even the SSH banners, or especially HTTP over TCP port 80, right, in the clear, that's where I start data mining. Anytime someone gives me a PCAP, I'm looking at clear text protocols first, because you can get the most information out of that with the least effort, right? And that's really what it's about. So when I see a file exchanged over HTTP, right, TCP port 80, I want to check it out. And so that's what this screenshot is showing, is the fact that, wait a second, I didn't just have one of these files that was interesting. I'm getting a whole stream of these files. So normally you'll see different software packages reaching out for updates or doing what I call online checks. They'll try to get maybe an empty text file, and if they don't complete the transaction, they'll assume they're offline. So typically if I see like a TXT file that has like a 0 file size, I know that's an online check. It's mostly benign, and I can tie that back to normally a piece of like update process or update software. So when I started to see proxy.pack files, first of all, I didn't know what pack was. And And Proxy, well, I was familiar with proxies, but as you will soon find out here in this presentation, I became a lot more familiar with exactly what proxy.pack was and how proxies operate. So when I saw the pack file, I was thinking, what the heck was a pack? And I add this to my growing list of interesting data to correlate and establish context. So now let's look at these files. One of the things I always do is anytime I'm looking at interesting traffic, I'm a networking guy, right? I got my CCIE 64908 in routing and switching. So naturally, I feel very comfortable at the CLI, at the Cisco command line, and I understand networks and how they operate, not by so much looking at the traffic at the PCAPs, but by understanding the IP addresses and how they become routed, right? And how data is shared across different networks. And so what I try to do is I go straight to BGP Looking Glass. One of my favorite BGP Looking Glasses is bgpstuff.net. It's made from a friend of mine, Darren O'Connor, at Melodrifter on Twitter. Go ahead, give him a follow if you're not already. All of this information I found out before class in some of the pre-conference trainings. I actually didn't know that you could include the MaxMind database in Wireshark and that you can get a lot of this information straight from that. So that while that's a really good reference and can help you at the packet layer, I wasn't even looking at Wireshark at the moment. I was still in Brim. And Brim can do some cool lookups as well, but MaxMind database is a database, right? So that's data, that's static data. So it's always reflective of what's in the past, while a BGP Looking Glass is telling you what the network is as of right now. So a BGP Looking Glass is always going to be a little bit more reliable when it comes to showing how networks are connected together. Autonomous systems and things like that change, and they can change between the time that MaxMind updates their database. Anyhow, that's just where I go. And I left this slide in here, even though I learned that we probably don't need it anymore. But it's definitely an awesome tool. And I want to make sure everyone is armed with the same tool set that I am. Moving on, same thing. So I took like the FQDN of those pack files I was looking at, and I looked them up in IANA's database, right? I did the who is. So I want to find out what company actually owns these IP addresses, or who are they registered to, right? That's going to help build some of this context I'm talking about. The same thing with the BGP Looking Glass at bgpstuff.net. It helps to build context, right? Before we jump in with a microscope, I'm trying to sort of even zoom out even more and take a look at sort of how these networks are connected to other networks globally, so I know who they are and where they are. Okay, jumping back into Brim, where we left off was I saw a bunch of HTTP requests for proxy.pack files. And I didn't know what they were, but there was a whole bunch of them. So Brim is a really awesome tool. Again, if I'm dealing with a large PCAP, I would typically run it through Brim first. What Brim does is it runs Zeek and Suricata through the entire PCAP. And what that does is it extracts tons of metadata. Zeek extracts tons of metadata, and Suricata, of course, is a signature-based IDS. So it's going to go ahead and give us alerts on things like malware and known file signatures and things. And what this does, why I do this for large PCAPs versus jumping straight into Wireshark, is it actually builds a database of all of this extracted metadata. So every time you need to build a new query or look at a new portion of data, a new piece of data, you're actually just querying a database. You're not actually reiterating over the PCAP itself, which is what you would do if you were in Wireshark. And this just saves time on large PCAPs. Also, I'm familiar with Zeek logs. I'm not an expert, but I'm familiar with them, and it definitely has a little bit of a learning curve. But once you start to build that familiarity with Zeek and Suricata, you can start to do a lot of these things a lot faster than Wireshark. And what's great is, again, this gives you the high level. And in Brim, there's a right-click feature, which is like pivot to Wireshark. So you can take any one of those things and right-click and pivot directly into Wireshark and begin that microscopic view of the bits and bytes, if that's what you're into. So we will be looking at Wireshark in just a minute, but we're still focused on that high-level view. What's interesting about this screenshot, right? I think I have the bullet points there. There are multiple hosts that are transmitting files back to what would be a Chromebook that's on my private IP space over HTTP, right? The MIME type is a clear text file, text plain. They're all the same file name. I want you guys to look closely. They're all the same total bytes, and they all have different hashes. So that's pretty interesting, because if a Chromebook or a computer or something is reaching out to the same server and getting the same file, and it's the same file size, there's normally on good suspicion that you're going to get the same file hash, right? It's going to be the same file. But this time, every single one of those is different. So that's very, very unique, I think. I can tell you why that is, but that's sort of part of this story arc we're building here. Okay, so let's actually take a look at one of these files, right? I was able to capture it right off the wire. Let's extract it out of our PCAP, open it in a text editor, and take a look. Okay, at the time, I didn't know what a proxy.pack file was. And so when I opened this text file, I was definitely like, what the heck are we looking at here? It's definitely code or scripts. I'm not a coder, and I can barely write a Python script. So when I saw this, I didn't even know how to understand it. I just knew that there was a lot of domains in here, and I didn't understand it. So you're always a little bit scared of things you don't understand. So should I be worried? At this point, should I start to panic? I wasn't really sure what I was doing. We've all seen the how hackers can trick you into downloading a script, and it makes malware run on your system. And then there's a command and control channel. And next thing you know, the whole network's ransomware. So I was really thinking, like, holy crap, what is going on on these devices? Well, at least that's the way they depict it on TV anyhow. So should I be worried? All right. So I think we've done a pretty good job of sort of setting the stage of what we need to do. So now we need to put our investigative hat on. We've seen some interesting stuff. Now we have some questions to answer, right? There's the who, what, where, when, why, and how, which are the 5 W's and an H. And I found this awesome image, which calls it the 6 W's. But that's not all. I want to always say, no matter what I'm doing, whether it's troubleshooting with Wireshark, troubleshooting a network, whether you're using Wireshark or some other tool, truth is just a perception of how you're looking at something. There can be many truths to the same story. So understanding data in context is important. And, trying to understand, is this a threat? Is this a problem? What do I need to do? We need to take all of the data points in context to understand what's really going on. So that's what I try to do as well. Okay, so I treated preparing for this presentation like a research project. My research led me to learn quite a bit about proxies, as ultimately that's what we're dealing with here. And this helps support the data in context, right? What are proxies used for? Generally, proxies are used for web-based traffic. Proxies can act at the layer 7 of the OSI model and normally do so. They can offer security through filtering and visibility. This filtering goes beyond the typical layer 3 or layer 4 ACLs you would see on like a boundary router or firewall. Today's modern next-gen firewalls often have the capability of running like a full terminating web proxy with TLS inspection built right in, and that's great. So this is pretty common actually, but not everyone turns them on. Proxies are one of the many capabilities that comprise enterprise security solutions like SASE, one of the new security architectures that a lot of big enterprises are going to, and secure web gateways, right? Which is part of that SASE security model. So again, I approached this like a research project, and for that, I needed to employ the scientific method as best I could. I did some research and I made a hypothesis. Based on the data I was seeing from Brim and what I started to learn through my research, my hypothesis was, is it possible to circumvent the web controls on a managed Chromebook? More specifically, by manipulating network traffic and only network traffic, right? Yes, I had the Chromebook sitting in front of me. Yes, I had credentials to log into it because I told my kids to tell me the credentials, but I actually didn't touch it. I didn't mess with any settings. I didn't go that route. Everything I did from the wire. So that's what made it fun. It's made it interesting, and you learned even more that way. Okay, so my next slide. Before we dive into all the packets from the research, I want to level set because I don't know what is the level experience of anyone who's going to see this. So I'm just going to assume that everybody knows nothing or knows a little bit about packets and about basic HTTP traffic. And that's what we're looking at here. So most, if not all of you, should be familiar with the standard HTTP GET request. This is one of the, I think, first real transactional bits of traffic that people learn about in their packet analysis journey. So we have sort of three columns. This is a bounce diagram. We have the client, the DNS server, and the origin server. Right. So the first thing before your client can even make a three-way handshake to a server, that's running a TCP server, TCP web server, it needs to make the DNS request. And this becomes pretty important for a lot of what we're going to see throughout my presentation. So first, your client reaches out to its configured DNS server and requests, does a DNS request for, in this case, it's site.tld, right? And your DNS server, if it's cached if it's configured locally cached, or if not, it will forward it upstream. But ultimately, it will respond with an A record if that record is found in the case of IPv4. Then your client can start establishing that TCP three-way handshake. And it's going to do that between itself as the source and the web server that the FQDN resolved. It's going to do that SYN, ACK, and ACK. That's the three-way handshake. Now, typically in a non-fragmented standard HTTP request, that GET request is your fourth packet. So that's one of the things you can kind of always just put in the back of your head. Anytime I'm looking at HTTP traffic that seems off for some reason, maybe it's in the fifth packet for some reason, maybe it's spanned, it's fragmented for some reason, but it should typically be in that fourth packet, right? And then the origin server acts that request and says, hey, I see your request. And it starts sending the data, answering that request, whatever that is. So when you're dealing with a proxy, that's this image now on screen. The transactions and the communication are a little bit different. You see, we've added a fourth column now. So we have our client, we have our configured proxy, the DNS server, and then the origin server. So we got our four elements. In this case, I'm using this is a bounce diagram, and this is generally based on an explicitly configured HTTP proxy from a workstation, just something very generic, right? The client is actually going to establish the three-way handshake between the proxy. Okay, so it's going to do SYN, ACK, ACK, and it's going to then make its request to the proxy. The proxy is going to receive that request and ACK that back to the source. Right? Then the proxy is going to go ahead and turn, and out its other side, it's going to say, wait, I just got a request for my website, showipinterfacebrief.com. Well, it can't go ahead and start a three-way handshake. It doesn't even know the IP address, right? All it did was get the host request from the client. So it needs to go ahead and make that DNS request to find out the IP address so that it can then establish the three-way handshake between itself and the origin server. The origin server, in case my web server, has no idea that it's dealing with a proxy and doesn't care, right? It's just answering the request that it gets, and it responds accordingly. Now, of course, it answers that request, and then in this case, the proxy acts that answer, turns around and hands that back down to the client, and the client acts back. So it takes, if you're following this, and we could have put a whole conversation in here, but it would have compressed everything so small you wouldn't be able to really see it that well. So this is pretty important because it takes 11 packets for the origin server to get the first GET request 11 packets, right? Where typically, if you're going straight from the client to the server, it takes the fourth packet is going to be your GET request if you take out the DNS server. With DNS, that would be 6 packets. And it takes a total of 14 packets for the client to receive its first byte. 14 packets, and that's a lot of back and forth for its first byte. So time to first byte can get pretty long there. You can imagine the packet latency if you were on the West Coast, VPNing into your company headquarters that is headquartered on the East Coast, because company policy is that you have to VPN in and there's a corporate proxy there that then you need to proxy to go back out to the internet, right? That latency can stack up a lot. And we're going to take some of those measurements here in some of these PCAPs. They're not so bad because I'm doing a lot of testing locally, but they can get pretty bad in extreme cases. So this makes a valid case for actually the shift that we're seeing in enterprise networking and security with the push to go SASE. One of the core components of SASE solutions pushes all of this to the big cloud vendors' edges at their POPs. So you're only ever going to the nearest POP for any vendor. Typically, there's a web proxy component part of SASE, and that sits on those big cloud vendors' POPs right at the edges. So if you're on the West Coast, you hit a West Coast server, and then you can go through your corporate policies as necessary. So it's a very interesting model way of doing things. And again, this pandemic has really pushed all of us to do everything from home, but also made all of us sort of security architects rethink how we implement security, because there's no longer the need to go back to HQ. And I'm sorry if my geographic references aren't relevant for our non-North American viewers. Okay, so let's let the fun begin, right? So now we have a basic understanding of how a proxy should operate using the bounce diagram, and we have a bunch of questions to answer. And we also need to prove or disprove our hypothesis. So, I kind of took this approach like, should I try to be as evil as possible and really push the limits on what I can do here, or should I be a nice guy, And instead, I just went where the data told me to go, and I'll show you what that is when we get to the end. All right, so what's the goal here? Again, I sort of made this a game for myself. It was a lot of fun. I love playing with packets. This stuff is fun. It is straight up fun. I didn't do this for my day job. I did this off hours at home because it's fun. So I wanted to affect the operation of the configured proxy. Now, affect the operation of the configured proxy is intentionally vague because there's a lot of different ways we could affect the operation of the configured proxy. And I really wanted to leave it open-ended. I didn't know where I was going to end up, so I didn't want to drive myself a certain way. So again, I imposed some rules on myself, which is cannot touch the endpoint configuration, and all effects must be from the network. So I can only affect the Chromebooks by using the network that's in front of me. All right, so a couple of baseline tests. So this is my control, right? Whenever you're doing a science experiment, you need to establish a control, right? Something, some sort of static variable that doesn't change. And so for me, I wanted to establish 3 baseline tests, or at least I thought that this would be a good way of doing it, of establishing 3 baselines. So I needed a workstation to go to a local web server using a local DNS, right? So this is going to establish what would be like known good 3-way handshake to over TCP/80, HTTP GET, simple stuff. Then I wanted to step it up a notch, right? Do one more, use the same workstation using an explicit proxy on the local network, making a GET request for an origin server. And third, from the same workstation using the same explicit proxy on the local network, making a connect request to a remote origin server. And to do that, I built a home lab. And when I say I built a home lab, what I mean is I just used my home network as is. I just added a VM. So I didn't actually have to build anything. Every network is my lab. Don't tell my boss. Okay, so I use this as a standard layout to perform the number of tests to establish the baseline. This also gives me a controlled look of how all the components should operate, right? The DNS, the proxy server, and a workstation. I hope this drawing makes sense because it's going to be the foundation of the entire presentation. So I have 3 hosts on a single VLAN with a default gateway that is NATing outbound to the internet. They're all on the 192.168.1.0/24 subnet, and their host IPs are shown next to their icons. Up at the top there, the north is my DNS server. I run Pi-hole here at home. And that's what I use to manipulate some DNS. Windows 10 workstation, that is actually the Surface Pro I'm presenting from today. I stood up an Ubuntu VM, and that's what I leveraged for a couple of different purposes. It's going to play a couple of different roles here. Sort of on the east side of that arm is my router gateway out to the internet. And of course, there's the ubiquitous internet globe all the way out on the east side. So my very first test, my very first baseline, let's make sure all of our systems can talk to each other, that they're configured properly, that we can control the software on each of the endpoints properly. This is your basic run-of-the-mill HTTP GET request to a local Apache 2 server. So in this case, my Ubuntu VM, I'm running Apache 2. I think I have like the welcome to Ubuntu static page that they have on there as a test page. And again, this is just setting the baseline for the control or our test environment. My Windows workstation is the client. It makes a DNS request for the FQDN of the web server. DNS responds with an A record. My workstation initiates a 3-way handshake to the web server and makes the GET request. Receives a response and closes the connection. Simple stuff. And I think what I'll do is I'm going to go ahead and open the packets on this one. Most people should have this available. If not, I hope a moderator will paste it in the chat or in Discord. I put out a little pack of PCAPs as a zip file, and there's those are my control PCAPs. So those are all within my own network. So I'm going to open up the first one if I can. And I'll try to share that to you guys on the screen. Can someone give me a thumbs up if they can see that? And if the text is large enough. So on Discord and Zoom 1, thank you. Dave Holt says good. Kevin S says yes, perfect. Thank you guys. Okay, so what I did here is I don't have any super cool profiles to share with you guys. I color coded these and also labeled them with hosts with resolved names just to get a context of the transactional conversation. The colors should correlate actually to the slide that sits behind here. DNS is blue, TCP and HTTP is green. So that's the purpose for the coloring. This same coloring model is going to go through all of my tests and then, of course, my actual experiment. So I keep with the same pattern to make it, I think, more understandable. So again, here, first packet is, of course, going to be our DNS request. From Pi-hole back to my client, the Windows 10 box is the response. I just went ahead and made an A record in my DNS server for proxy.wiresharkfest.acropolis.local is my little home FQDN. And for that host, I should say, we see here that there's the SYN/SYN/ACK, nothing special. The GET request, we're passing back a bunch of bytes. We're ACKing that. Then we're passing back, looks like 2 full payloads, 2.5 full payloads. And then my client goes ahead and says, got it. It actually unpacks this because I believe this is gzipped. I believe it's gzipped. Let me see. Git. Oh, it should be down here. Hypertext, let me see. Yeah, it's gzipped. So what the browser does is it receives that, it unpacks it, and it reads it. So what these first 3 packets are should actually be the HTML content of the page. And in that HTML content, it should be asking for an image. So the browser goes and fetches that image. It does this a couple of times and then finishes off with a FINAC handshake. So this is perfect. And again, this is very basic, no proxy inline, but we're going to use this sort of as a basis for comparison against our proxied connections. So, so what is the role of a proxy? And while I think there are many different kinds of proxies for many different kinds of protocols and data, architecturally, I believe they can all be placed in 2 groups. And I'd be interested to know if any other experts out there have a different opinion on this, but there are forward proxies and there are reverse proxies. Whether you're dealing with different data or different protocols or whatever, but they're in those 2 groups. Now, forward proxies make requests on behalf of the clients. Typically, you'll see this at a network boundary where there's many clients behind a single web proxy, an enterprise web proxy going out to the internet. Now, a reverse proxy receives requests on behalf of the servers. Typically, there are many servers behind a reverse proxy, and this functionality is normally combined with a load balancer. In fact, typically you'll see them sort of be one and the same. They have the same functionality. Sorry, I should have said that in this instance and in our test, we are going to be doing a forward proxy. All right, the browser versus system configuration. So how do you make your system actually talk to a proxy or route traffic to a proxy is the preferred terminology. Well, there's 2 general ways. As everything in IT, it depends, but there are 2 general ways. You can do it via your browser specifically. Chrome has a specific proxy configuration. Firefox has a specific proxy configuration. Internet Explorer, when that was a thing, actually uses the system settings for Windows. And OS level proxies. So if you're on a Windows system, I'm running Windows 10, you can configure a proxy at the OS level. And what that does is if your web browsers have a check mark, and in this screenshot, this is of Firefox, I think the use system proxy settings or the auto detect is typically checked by default. And so what that means is if your whole system is configured to use a proxy, then Firefox will respect that. It will find out what that is, and it will forward its packets. It will route its packets as necessary. Or you can exclude it from the proxy, from the system level proxy. Chrome also has the same features, but it normally respects the system proxy a little bit more. I don't know about Edge, and I don't have a Mac, so I don't know what the Safari settings look like. But as you can see here on the screenshot I took, there's a couple of fields when you want to go ahead and configure a proxy for like just your browser. Sometimes you want to test out a proxy. So you'll bring up 2 browsers. You typically use Chrome on this window and you use Firefox on this one. And this one's configured for the proxy. Or this is the one you browse Facebook on, and this is the one you do your work from, whatever it is. All right, so there's a couple of boxes in there. The first one that has the red highlighted rectangle around it has 2 input boxes, HTTP proxy and HTTPS proxy. You have a space for an address and a port number. This can be an IP address or it can be an FQDN. If it's an FQDN, obviously it has to be resolved first before you can then send route your request to your proxy. Sometimes this causes some initial delay for those people who have proxies in their enterprise at their boundaries or just testing them out. If that's the case, and in the morning, every time you open up your computer, besides it doing a ton of other things, it's also looking for it's trying to resolve the FQDN for your proxy so it can begin to open your web pages. Actually, so it can begin to send the request to the proxy so the proxy can request those for you. So this gives you the ability to sort of separate out your traffic. If if you don't have the secret keys, if you don't have the transaction keys for HTTPS traffic, there's almost no point in proxying it. There's a little bit of visibility you can gain from it, but if you have a proxy in line, you can probably derive visibility from other tools in your network. If you've invested in a proxy, you've probably invested in other tools as well. I'm making that assumption. I want to step down to the second red box there, the one called automatic proxy configuration URL. So this is where you would put in your PAC file. Now, PAC, P-A-C, stands for proxy auto configuration file, I think, auto config file. And so what you're doing is you're telling your browser where that file is, so that when you fire it up in the morning and you put in facebook.com, first it grabs its PAC file and then assesses whether or not the FQDN you gave it needs to be sent to the proxy or not. All right, your system settings. Again, I'm on a Windows system. I use Windows 10. I have a Surface Pro. So here you pull up your internet. I think it's called Internet Options in the control panel. There's probably 100 different ways to get to it. You go to the Connections tab, and down there's a button called LAN Settings. And the new window that pops up is very much just like the Firefox one. It gives you the ability, the first red box on top is where you would put your PAC file. And there I just put example.com proxy proxy.pac. And below that is where you would put an explicit proxy. So that's important, right? Because both of these have the same thing. So there's explicit and then using a PAC file. And there's a big difference there. Actually, I think that's my next slide. Or is it not? No, I'm sorry, it's not at the moment. So that's where you make your two settings, and then your system will be configured, your Windows system. So most applications on your system that are making calls to the Windows operating system that say, hey, I need to go out to the web and I need to go to this URI. Windows will actually tell it to use this proxy if it respects that or not. Even if you have a proxy configured on your system, not all software needs to respect that or will respect that. So I want to talk about the PAC files, because there's explicit configs or there's PAC file configs. And the difference is, if you explicitly send traffic to your proxy, you're sending everything to it. That would be the case here on this screenshot, the lower red rectangle, where I'm putting in an IP address and a port. And what that's saying is to send every web request that I put, I guess if my browser is using my system settings, put every request, send it to the proxy. Now, the one on top is where you put the PAC file. And that's often a little bit a better way. Well, I guess better is subjective. It's a different way to do it, and it has some advantages, and I'm going to talk about some of those. So what does a PAC file look like? The anatomy of a PAC file. I actually grabbed this screenshot because I modified the one that I pulled off the wire from my kids' traffic. And it's actually probably 5 or 6 pages long. And I just pulled out just a couple of things to simplify some of the operations, because it's actually very important here. It starts off by a function called find proxy for URL, and then it gets passed in the host. So there's normally some sort of logic in here, right? There's an if statement, and it'll say something like, if your host matches this, in this case, it's msftncsi.com, which is Microsoft Network Connectivity Status Indicator. This is how Microsoft knows if it's online or not. It fetches a text file from there, I think called nsi.txt. So what this PAC file is saying, what this example PAC file is saying, is if your host is msftncsi or star.msftncsi.com, send that direct. That means don't send it to the proxy, send it directly from the client, send it directly to the server. Have the client resolve it, do the three-way handshake, and just carry on like it normally would. Don't send it to the proxy. And then that's the first return there. The second return acts sort of like as your else statement. If it doesn't get directed and it doesn't match, return it to proxy, which means actually proxy that connection. So why would you do something like this? Well, you do something like this if there was like maybe a trusted application that you were allowing people to browse to, either for performance reasons or because that application actually won't work through a proxy. You know, some video that's done over HTTP might not actually work through a proxy. I'm trying to think what else. Also, it might be a sort of a trusted vendor. You know, maybe you really trust Office 365 and anything with any of the Microsoft FQDNs, just send it straight to Office 365. But anything else like Facebook or Snapchat, or I don't know if Snapchat has a website or anything, actually send those through the proxy. You know, we want to make sure we either check them for URL filtering and content filtering. So I think I already mentioned the explicit versus pack. So a pack file is a Java-based logic file, which decides which requests get sent to the proxy and which should be sent directly to their origin servers based on a series of if statements. So explicit, everything goes. Pack, when you're configuring your system or your browser for a pack file, it's like saying, if you're managing like maybe an external proxy and you're hosting the pack file, it's like saying, come and grab this pack file every so often, and I'll update it for what I want you to send to the proxy and what I want you to send directly to its destination. So it gives you a bit of logic in there, and it lends itself to scaling much better. Could you imagine if you had an enterprise with hundreds or thousands or tens of thousands of endpoints that all needed to use some sort of enterprise boundary proxies? If you had an explicit one and you needed to add a new exception, you'd have to do that through group policy. Group policy is only a Windows thing. How do you do it on the Macs? How do you do it on the Linux systems? It becomes a mess. But if all of the systems are configured to use a pack file, you just edit that in one place and all the systems will grab that new pack file either every so often or every time they boot up. So this lends itself to scale much better. And you would think like MSSP, I put in the slide there for like managed security services provider, SASE, secure web gateway type stuff. I'm talking a lot because I don't have anyone here to interrupt me. So it's just me. So for my next test, I configured my Ubuntu VM, which is running Apache 2 as a forward web proxy. It's making requests on behalf of my client. This is demonstrating a standard HTTP GET request using plain text or clear text HTTP. And you can see there, as we step through it, I'm actually just going to pull up the PCAP and let's take a look. That's what we're here for after all. All right, so this one follows the topology I just had on the screen. Make sure I'm scrolled up here. Okay, so for this one, again, my coloring in this profile is not anything specific. It is just, well, it is something specific, but it isn't anything cool. It's just to match the flow arrows in the topology. So first you see the client reaching out to the proxy, doing a three-way handshake, sends an ACK, and then sends its GET request, just like it normally would. There's nothing special about this. In fact, if we open it up, you can't see anything different from this GET request to any other GET request. It's as if it was making it directly to the origin server. And then the proxy acts that request. Now, what's interesting here is the proxy needs to actually know what is the IP address for http.com for this host that I'm looking for. What is that IP address? No one ever told me. So the proxy needs to make that DNS request and resolve that so that it can make the three-way handshake to the actual origin server. And that's what you see here. You see the DNS request, DNS response, of course, the three-way handshake, and then the GET request. So what I thought was kind of interesting here is there's a new header that got added by the proxy, right? This is a header via, or I guess via. 1.1 is the HTTP protocol it wants to speak. And then it's indicating an IP address itself and the port. And actually, this isn't actually on by default. I went through my Apache 2 configuration and I turned this on because I was using a how to turn a VM into a proxy guide. And I was just following along. And then I realized that this was actually turned on by me. But there's a reason that this is actually turned on. And I've seen this in live captures before, not knowing exactly what it was or what it was there for. This is there in case of proxy chaining, in case this proxy is actually sending traffic to another proxy. It needs to know where to send the traffic back to, right? It needs to know that there's another proxy in line. And so that's what that's actually for. There's a couple of different options to turn it on or off, and it's on by default. So typically when you see this, it has been added by a proxy somewhere in the line. Okay, so the proxy makes the request to http.com. It's funny, I actually struggled to make this capture so many times because there aren't a lot of HTTP servers out there on the internet. Most jump right to HTTPS or quick. So I actually found one, and I don't recommend going to this site. They end up redirecting you to another site, and it's a bunch of crap, but at least I found one. So I'm thinking about taking it on myself of hosting like a standard TCP port 80 HTTP website that just says this is HTTP, you know, something that everyone can use for testing. All right, so it sends its response back, and it includes a couple of things. You know, you get to see like, this looks like an IP load balancer. IP load balancer, this is added from the server coming back from http.com to our proxy. Our proxy acts that and finishes the handshake. And then it sends the packets it just receives down to the client. And our client acts that back. So if we just take a look in here, we see everything here. We even see the via header being passed back down to the client. So on the client side, if you were doing a client-side capture, you would be able to see it. I guess maybe this is proxy specific or implementation specific, but you would see that. And I'm going to move on for the sake of time, but this is pretty basic, right? So it sends the GET request. The proxy makes that request on your behalf, receives the data, sends it back to the client. So it really acts as a true intentional man in the middle. My next slide, I wanted to point out, Jasper, don't hate me. I put packets a la trace wrangler. So what I did is I didn't know, what I wanted to share with everybody and everything. So I started running some stuff through Trace Wrangler, which is Jasper's tool he makes, and I've used it. Oh, I'm sorry, I have my Wireshark up. There we go. I've used it many times, so I ran it through, and what I found was the anonymized version, which is here on the right side, actually doesn't anonymize the via header. So I kind of remember this from an old PCAP CTF that I played actually with Saka for CloudShark. Where's my CloudShark stuff? CloudShark. We miss you, Tom. This is my PCAP. They anonymized their data in a PCAP, in a CTF PCAP challenge, and they used Trace Wrangler, and it left some of the HTTP header fields untouched. So I think by default it does this, and I know there's sort of like a regex feature where we can just go through all the payloads and change certain values. So I could write a regex for the hex match of this and change it to a different IP address. But I just thought that was interesting, and I wanted to bring that up in case Jasper's watching. So maybe add in a little checkbox for HTTP headers as well. And a word about the via header. This is an Apache specific configuration. Here's how you turn it on, off, full, or block. In the sake of time, I'm going to move on. All right, so what we've done so far is a basic GET request, a basic GET request through the proxy. Now we need to do an HTTPS connection through the proxy. And it's interesting to do this because it mimics very much what you see in the HTTP proxy, the one I just showed you. But if you compare that to what you know about HTTPS, right? The HTTPS GET request between a client and a server happens after the TLS handshake, right? That's actually encrypted inside. So we can't actually encrypt from the client through the proxy to the server because the proxy has no idea what server you're trying to get to. So there's sort of a chicken and egg order of operations here. And this is why they put that HTTP connect message on the outside so that you can see it. So what happens is the Windows client wants to establish a connection to an HTTPS website, three-way handshake to the proxy. Proxy receives that request as a connect statement. Now the connect verb, the HTTP verb connect, their method, is indicating that it just wants to make basically a TCP tunnel and that we're going to do this over HTTP. And in that HTTP header, that connect method, it also says the FQDN, the full URI of the website I want to go to, whether it's Wireshark.org. I guess Wireshark.org is quick now, but yeah, so if it's Wireshark.org, so that the proxy can then make the proper DNS request, get the IP address, and then start its three-way handshake. And that's what you see here, right? It starts a three-way handshake with the server, and then it acts that back to the client and says, okay, I got my three-way handshake with the server, connection established. Now what do you got? So then the client goes ahead and sends its TLS client hello, and that actually gets proxied through, but it's almost proxied through completely untouched. It's received by the proxy on one side, repackaged, and sent out the other side. And what you're actually doing is you're making a TLS tunnel between the client and the origin server through the proxy. Of course, once that TLS session is established, then you can make your HTTP GET request, which is what you would see in a decrypted session. And it just so happens that packet labeled 03 is exactly that. It's HTTPS through the proxy, and I've decrypted it for you. And the keys are already in there. So again, I've used all the great Wireshark videos to learn how to embed keys and only the specific keys for these specific connections. Again, I keep them labeled and colored specifically. The green connections are between the client and the proxy, blue is DNS, and red is between the proxy and the origin server, labeled as such. You can see here the client hello gets acked by the proxy and then spit out the other side and gets sent to the origin server. In fact, if you pull up this client hello and that client hello, they're almost the same byte for byte, right? It's completely unchanged, and it has to be in order to establish that TLS tunnel, because I'm not doing break and inspect on this guy. It would have resulted in an untrusted certificate anyways on the final Chromebook. So I'll let you guys dig through that, but I wanted everyone to have these samples: basic GET request through the proxy, and then a connect request through the proxy as well. So those become your baseline. Add that to your baseline library of PCAPs. Excuse me. I need to get moving because I'm way over time. So why is there a proxy to start with, right? URL content filtering. In the case of my kid's school, I'm pretty sure it's just liability, legal liability, logging and visibility. The school provided all the students with Chromebooks for school from home, and they can't just be wild and free exposing our children to all the naughty bits that are on the internet. So I really think this becomes an accountability and liability reason, and not really content filtering. But in an enterprise environment, actually, it's probably the same. So what's being blocked? I tested just a few things. I didn't want to get anyone in trouble. Cartoon Network is blocked. My website, showipinterfacebrief.com, is blocked, and malware.com was blocked. 1 minute till Q&A time. Oh no. Cartoon Network. What's interesting about this one is contrary to common practice, the Chromebook is actually making a local DNS request first. I actually learned today through doing more research as I was preparing for this, that's because of some of the language in the pack file that's actually on the kids Chromebook that is actually checking for the resolved IP address first before it makes the decision to send to the proxy or to send direct. So every request it gets, it's telling the Chromebook, go ahead and get the DNS reply. And then if the IP address matches one of these, we'll send it direct. So that's not the loophole I found, but that's why it was making DNS requests, because it doesn't have to make the DNS request first. The DNS requests have to come from the proxy server itself. This is what I found. Cartoon Network, connection reset. This is just sort of a generic reset page. I went ahead and did my blog, right? My blog, the .com actually refers you to github.io, where I host my site. And of course, that one also blocked. But it's not just these generic reset pages. They also can give you a block page, what you would expect from a company. So all of my research was based around these three attacks. So I have a few domains that I know are blocked, Cartoon Network and at least my blog. So let's see if we can work our way around this using only the network and not touching the Chromebook. The three ways I thought that might be most feasible: black hole the pack file domain. I control the DNS. I'll just black hole it so it can never get the pack file and it won't know that it's supposed to proxy anything. In fact, most systems will fail open. The second was hijack the pack domain via DNS and resolve it to a server where a malicious pack file can be hosted, but that malicious pack file is just a little less restrictive. And third, use the pack logic against itself. So black holing the pack domain didn't work out. That was quick. So there are policies that say you have to be able to reach your proxy or don't connect to anything. And that just so happens to be the policy on the computer I was testing. So moving on to option 2. Hijack the pack domain via DNS and resolve it to a server where a malicious pack file can be hosted. So before I show you what I did, this is how it should look in a lab environment, I guess, in a in a controlled environment. The Chromebook says, where can I get my pack file? DNS says, I'll forward your request and get an answer for you. All right, it returns the response. The Chromebook reaches out to an external server. In this case, it's vendor's cloud, downloads that pack file and receives it. Once it has the pack file, it now has the logic to decide what needs to be proxied and what needs to be sent directly to the web resource. Pretty basic. So what I'm going to do is I'm going to insert myself right there at I don't know if you can see my mouse, but right here at the DNS server. So again, the Chromebook is going to ask, where can I find my pack file? And my DNS is going to respond, hey, show IP interface brief has it for you. Go check his IP address. And I just am using this as a conversational language, but I gave it an IP address for a server that I was actually hosting up in the cloud. So the Chromebook reaches out to my server and I'm hosting the pack file for it, right? I know what it's looking for because I've seen all these requests before in my research. So I deliver it what I call a wide open pack file. And here's what I gave it. You guys remember about 10, 15, 20 slides ago, there was a find proxy for URL. I gave you sort of a pack file anatomy. In this case, I'm returning everything direct. Send nothing to the proxy, send everything directly to their destination, which kind of results in all the traffic just being forwarded like it normally would. Straight from the device under test, straight out to the web if that's where the resources were. So in that case, remember, I was testing at least 2 domains. I was testing Cartoon Network and my blog. Let's take a look. First test, Cartoon Network, got it. All right. And I'm trying to breeze through this quickly. I know I'm cutting into Q&A time. I only see one question up there. So I hope you don't mind if I just keep going, and I will definitely answer that question, Kevin. I see you. If we take a look at these packets, again, you know my color scheme, right? I'm doing DNS is blue, all other traffic is green. And remember this case, I'm sending everything direct. I'm not involving the proxy at all. So all that traffic is green directly between the client and the server. You can see the 3-way handshake. It's a full TLS connection. Nothing unique about it. You guys can go to cartoonnetwork.com. You can generate your own PCAP, look exactly like this. Now let's check my blog. Boom, 2 points. All right, so now we've sort of successfully implemented a bypass. It's pretty cool. Not time to celebrate yet, but we can give ourselves a pat on the back. And those packets, again, look like this. You can go to my blog website. You can go to my domain and create your own PCAP. Looks exactly like this. There's nothing special about it. But that's cool. We were able to sort of circumvent the proxy controls without touching the endpoint. And but it's not super hackerish. It's not all black hat, right? But it's just being able to observe the network, right? Via the lens that our tools give us, sort of understanding what's going on and sort of what weak points are there. And it's not a technical exploit. And I'm going to talk about this in just a moment. Our third option was using the pack logic against itself. I'm almost done with these slides here. Truly, I am, if I have just a few more minutes. This was something I was looking forward to. I'm glad I tested it, but sadly, I will tell you this option number 3 did not work out for me. So this is an excerpt from the actual pack file I sniffed off the wire. You can see in the red highlighted area, there are 2 domains in there, one for msftncsi.com and then star.msftncsi.com. And what this means is anything that is just msftncsi.com, so no www, no dot, no nothing, just http://msftncsi.com. Or the second, what am I trying to say? Not variable. The second host in that list has the star dot. So that's going to take care of all of the subdomains, right? And possible subdomains. What I was hoping for is that I would find a misconfiguration in the proxy in the pack file. What I was looking for was an example that I have there, which is just star msftncsi.com. What that would allow us to do is, first of all, that would match on anything, whether it's www dot, whether it's news dot, or whether it's just Tony is awesome msftncsi.com. So you can just go register a new domain and it would get bypassed. It wouldn't go through the configured proxy. That actually didn't work out. I didn't find any misconfigurations. That's the way the cookie crumbles. So that's the end of the possible pack attacks. I came up with 3, and it didn't work out for me. I had a crisis yesterday or the day before where I realized I actually did all of this research, all of these tests, all of these PCAPs, all of the screenshots, and I realized what I was doing had an invalid character in a FQDN that I stood up locally. And so I was panicking to get everything done again for this presentation. I used an underscore. Underscore is an invalid character in an FQDN hyphens only. I was using an underscore just to make sure that no other systems would accidentally stumble across it, not even thinking it was an invalid character, and it was. Lesson learned. Also, this entire sort of premise that I've built on this flaw that I found or vulnerability is based on one assumption. And the assumption is that your gateway is more permissive than your proxy server. And this is the case for a lot of places, maybe not typically an enterprise, and certainly not a enterprise that favors security. So yeah, in the case of my home, yeah, the proxy server was blocking a lot of things, Cartoon Network, my blog, whereas my gateway, I'm not blocking those sort of things. So is that even a vulnerability? It depends. 3 takeaway slides, and then we're done here. I only have one question. If you guys have questions, go ahead and ask. Takeaways part 1, just because something is proxied doesn't mean we can't see it, play with it, and manipulate it. We absolutely can. We've proved it here. If we were going to get even more scientific, maybe we would try manipulation for data in flight, actually changing requests in flight. Maybe there's a part 2 for next year. I don't know. And this is not exploiting a technical vulnerability. Rather, it is exploiting an implied trust. The Chromebook trusts the DNS that it gets from DHCP. It trusts the pack file server hosts that it's delivering, that it's downloading the pack file from, and it trusts the data in the pack file, right? There's absolutely no validation or authentication. And in fact, I think in the spec, there can't be, because you run into a chicken and egg problem. So I think it almost always gets that in the clear. I see Sherry sent me something, 5 minutes left till Zoom ends. Awesome. I have just these 2 slides. I couldn't have said this better. This came straight from the Chromium source code, a write-up for the proxy capability. Well, actually, I'll let you guys read it. I'm short on time. This is absolutely perfectly well stated. Definitely take a look. There's a ton of information on that page. Follow that link at the bottom. Another takeaway is, if you control DNS, you control everything. You can deliver untrusted packs. You can do all kinds of stuff. If you control the pack file, you can avoid the proxy, exposing a possibly less secure communications channel. In this case, your proxy super secure, your gateway is a little more permissive. And if you read the pack file, you can gain a little intel. You can use that data against itself. So all in all, I consider this a reason to celebrate. I consider my hypothesis proved. It is possible to circumvent web controls on a managed Chromebook using only the network. And here are some awesome resources. Definitely take a screenshot of this and take a look at the Gerdog weird proxies there towards the bottom. Awesome research coming out of Russia. So that's all I have. I have one question. Do you have a list of recommendations for folks who want to deploy security on their home network? Pi-hole, firewall, SIM, Brim. Thanks. Oh my gosh, so many recommendations. I used to do a live stream where I would give samples of all the stuff that I have on my network and talk about it. So yeah, you can reach out to me. I love this stuff. I do it for fun. So I'm happy to talk your ear off. And for all you TCP fans,